In the first question, we have a tangent and a secant drawn to the circle. We know that when a tangent and a radius to the circle meet, they're perpendicular, meaning that they form a 90-degree angle. So what we have here is we have a right triangle. If AC is 20 and OA is 7, we need to find the length of OC. So all we need to do here is use the Pythagorean theorem. A squared plus B squared equals to C squared. 7 squared plus B squared equals to 20 squared. 49 plus B squared equals, definitely use a calculator, 400. From here, I'm going to subtract 49. And then I'm going to take the square root. And it does say to the nearest centimeter. So it's not going to work out exactly. And that's about 19. In the second one, we have tangents to the same circle that come out of the same outside point. So these two tangents are equal to each other because they come out of the same outside point. These two tangents are equal to each other because they come out of the same outside point. And these two tangents are equal to each other because they come out of the same outside point. We know that AB is 20. We know that A is 12. So that means AD is also 12. And wait, if this whole thing's 20 and this is 12, that means that this piece is 8, and that means that this piece is 8. And we know that CF is 15. So this is 15 as well. And so the length of AC is just 12 plus 15, which is 27. For this one over here, we're given arc DE, which is 136 degrees. And we're given the measurement of angle C, which is 44 degrees. We need to find the measurement of arc FH. So we have an outside angle. And remember, the outside angle, any outside angle, could be formed by two secants like we have here, by a tangent and the secant, and the outside angle. The outside angle equals to half the difference of the intercepted arcs. Big intercepted arc minus small intercepted arc. So here we know the outside angle, we know it's 44 degrees. And I know the big intercepted arc is 136 degrees. But what I don't know here is the little intercepted arc. So I'll represent that as x. I'm going to start off by multiplying both sides by 2 to get rid of the 1/2. 44 times 2 is 88. And that's equal to 136 minus x. I'm going to subtract 136 from both sides. And that's negative 48. I'm just going to come over to the side here because I ran out of space. And then to get the x by itself, we'll just divide by negative 1. And we have x is equal to 48. And that x represents the small arc. And we can test it out if we subtract 136 minus 48. And then we half that, we get the outside angle. So it does work. for this one over here, you should really draw a picture. We have circle O, and that means that O is the center of the circle. And it tells us that points A, B, C, and D are located on the circle, so it's inscribed in the circle, forming trapezoid ABCD, with AB parallel to DC. Which statement must be true? So if we have parallel chords, like we do AB and DC, they intercept congruent arcs. Just to show you a smaller picture of that. Parallel chords intercept congruent arcs. So the arcs that they intercept are the ones between them because it's the ones that the chords endpoints are touching. Alternatively, if the chords are like this, that are parallel, touching, 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 those would be the intercepted arcs. So let me see for here, because these arcs are the ones that are in between the parallel chords that are congruent. Let me see if arc AD congruent to arc BC is an answer choice, and it is. AB congruent to DC, that's not true because a parallel does not mean congruent, and we don't know that AB and DC are congruent. If we knew that arc AB and arc DC were congruent, then we could say that because congruent chords intercept congruent arcs, but we don't have any information about those arcs, so we can't say that here. Angle A congruent to angle D, that's actually not true in a trapezoid. In a trapezoid, since we have these parallel lines, the top and bottom angles right underneath each other are same side interior angles, and they're supplementary to each other. So in any trapezoid, top and bottom angles are supplementary because they're same side interior angles. AB, arc AB is congruent to arc DC. We have no way of knowing that. If we instead knew that chord AB and chord DC were congruent instead of parallel, then we would know that because congruent chords intercept congruent arcs. But right now we have no way of knowing that. Okay. We have intersecting chords, and it says which relationship must be true. And these are all about segment lengths. So here we just have to remember our theorem about segment lengths of intersecting chords. And it's part times part of one chord equals to part times part of the other chord. So on one chord, the two parts are PT and TQ. And the parts are from one endpoint to where they intersect, from one endpoint to the point of intersection of the chords. And then we have the two parts of the other chord. And that's this answer choice over here. It was the only one that had a product correctly written, or written at all, I should say. Okay, the measurement of arc AD. I need the measurement of this arc because our theorem is that the inside angles, the vertical angles created by the intersecting chords, is equal to half the sum of the intercepted arcs. Let me just get a little bit more space over here. So I'm going to write that here. The inside angle, you can also think of it as the vertical angles created by the intersecting chords. The inside angle in the circle is equal to half the sum of the intercepted arcs. So Since we are using this arc and we have this set of vertical angles, this is the other arc that we need because the other vertical angle opens up to this arc. But unfortunately, we have the 124. So in order to do this, I'm going to need to find what arc ML is. But luckily, MD is a diameter, P is the center of the circle, and we know that for sure because it does say circle P, which means P is the center, and it does say diameter MD. So that means from D to M is halfway around the circle, and that's 180 degrees. So if I do 180 minus 24, I get 156, which is the other arc. And now I can plug into my theorem. The inside angle, which we know is 46 degrees, is equal to half the sum of the intercepted arcs. So one of them is 156 degrees, and the other one we don't know, it's x. If I multiply by 2 on both sides to get rid of the 1/2, and feel free to use a calculator, 46 times 2 is 92. When in doubt, use one so you don't make a mistake. Equals to 156 plus x. Oh, sorry, I wrote 156. That was supposed to be 56. 180 minus 124 is supposed to be 56. I'm like, that does not make 180 degrees. And I would end up with a negative number here. That doesn't make sense. If we're seeing an arc on a circle, it needs to be a positive number. It can't be negative. So let me change that over here as well. Okay, now let me do 92 minus 56. And we have 36 degrees. There we go. Okay, is there any more multiple choice? Let's check that out. No. Okay, let's check this out over here. So for the givens, you don't need to write every single thing down, but a lot of you guys miss half the givens here. So we do need circle O. We do need diameter AOB. We do need that we have tangent CB. So I don't need to write every single word, but I do need all the information. And on the Regents exam, they will take off points if you don't have all your givens. And BE is parallel to ABC. And those are my givens. In the diagram, I want to mark this. A lot of people have not been marking their givens, and then you can't see things. When you have parallel lines, I'm always looking for angle relationships, and here I see my letter Z. And then the corners of my letter Z are alternate interior angles. And the reason why that's helpful is because you're proving the triangle similar. And we know that 99% of the time, you're going to be proving triangle similar by AA. I just want to take this moment to remind you guys that there's only 3 ways of proving triangle similar at all. There's AA, there's SAS, and there's SSS. But in order to use the ones with the S's, you need side lengths because you need to be able to tell that sides are proportional. Remember, in similar triangles, the S's are proportional sides. In congruent triangles, they're congruent sides. So many people were proving triangles similar using HL or ASA or AAS, and that doesn't work because those are not one of our ways of proving triangles similar. So whenever you see that triangles are similar, it's always going to be AA. And that gives you the last step of the proof already. Even if I don't know the stuff along the way, that's AA. And then a lot of people before this or after this, I don't even know, were saying, we're writing a proportion and saying corresponding sides of similar triangles are proportional, or writing a product and saying the product of the means equals the product of the extremes, but it didn't ask you for that. The proof statement is just to prove the triangle is similar, so you didn't have to do any of that, right? If the proof statement's not asking you to prove a proportion or a product, you don't need to do any other steps. Your proof is over when you prove the proof statement. So I already got one congruent pair of angles to prove my triangle similar. And I'm going to put that down in my proof. So I'm going to put down angle CAB is congruent to angle ABE. And I'm going to write my reason down. Alternate interior angles are congruent when parallel lines are cut by a transversal. You do need to include the part about they're congruent because lines are parallel, because alternate interior angles are not always congruent. They are only congruent when you have parallel lines. Next, I need to find another pair of angles for AA. And even if I'm not sure how to get it, the nice thing about circles, unlike other topics, is that what you think is true, there's often a way to show it. It often is true. And for me, looking at the diagram, I think this is going to be a right angle, and I think this is going to be a right angle. But I just need to figure out a way to show it. So I'm going to start with this right angle first. And it told me that CB is a tangent to the circle in the givens. And it told me that AB is a diameter. And remember, when a tangent and a radius, or a tangent and a diameter, meet, they're perpendicular. So I'm going to put that down over here. Segment CB is perpendicular to AB. You can also do OB if you just wanted to do the radius. A tangent to a circle and a diameter are perpendicular where they meet. And then I can say that angle CBA is a right angle because perpendicular lines form right angles. And that takes care of this right angle. Now I just have to justify why this one's a right angle. I saw so many people saying the triangles are right triangles. You only need to say that the triangles are right triangles if you're using HL, because HL requires right triangles, or if the proof statement is to prove a triangle is a right triangle. Here, we're using AA, so we just need congruent angle pairs. So we just need to, after we show that these are right angles, we just need to say they're congruent to each other to have congruent angle pairs. You don't need to state that you have right triangles. It's not wrong. It's just unnecessary. It doesn't help you. It doesn't get you points, but doesn't take away points from you. The thing is, though, if you do say something that is incorrect, it does deduct points from you on the Regents exam. Even if the other stuff is right, if something is incorrect, it does deduct points for you on the Regents exam. Okay, number 5. I'm going to talk about this right angle. And I see that this right angle, well, I think it's a right angle, that this angle is an inscribed angle that intercepts the diameter, or a semicircle. Any way of saying that. And the inscribed angle that intercepts a diameter is a right angle because it opens up to 180 degrees. Half of 180 degrees is 90 degrees. So I'm going to write that down. Angle AEB is a right angle and inscribe angle that intercepts a diameter or a semicircle, that just means half a circle, is a right angle. And finally, I do need congruent angle pairs for AA. That means one congruent pair of angles, two congruent pair of angles. We already had one congruent pair of angles from the alternate interior angles. And even though I've now showed that I have two right angles, I then actually show that they're congruent to each other. So that's where I'm going to do this. The two right angles are congruent. And we know that's because all right angles are congruent to each other. They're all 90-degree angles. They're all congruent to each other. Over here, we have a tangent and a secant, so we have outside segments. And remember, it doesn't matter the combination of outside segments as long as you have outside segments. And if I put the information into the diagram, I'll see that it gives me segment lengths, and it's asking me for the length of segment AL. For outside segments, when you're talking about lengths, the theorem is whole times outside of one outside segment equals whole times outside of the other outside segment. Let's start with AE. The whole AE is 36 plus 12, which is 48. And the outside part is 8K, which is 12. For the tangent, the whole is AL, which is X. You don't know what it is. And the part that's outside the circle is the whole thing, right? There's no part of a tangent that's inside the circle, so the whole and the outside are the same. So that would be represented as X once again. I'm going to use a calculator, 48 times 12. And I get 576 equals to X squared. I'm going to take the square root and see if that works out nicely. And it does. Always nice when it does. And then we don't have to worry about simplifying radicals. And we have that X, which represents AL, is 24. Okay, moving down to the next one. In order to convert this equation into the regular equation of a circle, where we can clearly see the center and the radius, because remember, HK is the center of the circle and R is the radius. So in order to get it into this format, we do need to complete the square. I'm going to group the X terms together, and I'll leave a box because I am going to have to add something there. I'm going to group the Y terms together, and I'll leave a box. I'm going to move the constant without the variable to the other side of the equal sign. And remember to keep my equation balanced, whatever I add on the left, I also need to be adding on the right. So I'm going to make boxes so I don't forget that. To find the term that completes the square for the X terms, I'm going to do B over 2 squared. A, B, C, which we're finding. So our B coefficient is 16. So that's 16 over 2 squared. So that's 8 squared. And that's 64. For the Y terms, and I'll just do that at the bottom over here. B over 2 squared once again. A, B, C. B is 12. 36 is the number that completes the square. Now we need to factor. And remember, it's going to factor to the same factor repeated twice. Same thing over here. It's going to factor to the same factor repeated twice. And the easy trick for what it factors to is the B over 2 before we squared it. So here the B over 2 before we squared it was 8, positive 8. And here the B over 2 before we squared it was 6, it was positive 6. On the other side, let's add the numbers, 44, 64, and 36. and we get 144. So the center of our circle is -8, -6. Remember, in the equation of a circle, since there's the built-in negatives, if you're seeing a positive here, that means it started out as a negative, and the double negative made it the positive. So when you're pulling out the center from the equation of the circle, always think the opposite sides. And then remember this side is r squared, as you can see over here. So r would be radical 144, which is simply just 12. So here the center of our circle is -8, -6, and our radius is 12. Let's check out this next one over here. They marked the lengths for us in the diagram, and we're told that diameter AC is perpendicular to chord BD. When a diameter is perpendicular to a chord, it bisects the chord. Okay. And that's really helpful because if we find one of the sides, we can find if we find like ED, then we have BE, or if we find BE, then we have ED, and then we can just put them together in order to get BD. OA is the radius of the circle, and so is CO. So I know that they need to be equal to each other. They both need to be 5. Since I already have the 2 part over here, that makes EO 3. And now if I just take a look at this right triangle, you might see it's a 3, 4, 5 triangle. But you can use Pythagorean theorem to figure that out. But it is a Pythagorean triple. And then you know this is 4, and the length of BD is simply just 8. Okay, this one was just to construct an equilateral triangle. This one was easier than the one on the review sheet because the one on the review sheet was to construct a hexagon, and they're the same construction. The only difference is that when you get your hexagon construction, instead of connecting all the points together, all 6 of the points, you're just going to connect every other point. So you're just going to connect 3 of the points together, but it's the same construction. And the one on the review sheet, you had to, determine with the chords what kind of triangle it was, and it was a right triangle because the inscribed angle intercepted the diameter. You don't have to do any of that stuff here. So this one was much easier. And in the video for the review sheet, I did mention how to turn your hexagon construction into an equilateral triangle because it was going to be on the test. So that was in the video and in Regents Review number 4. And mine's not going to be that accurate because I'm on the computer and I hate doing this on the computer. It moves, I can't get it exact. Yours will be much more accurate than mine. So I just put my compass on the center and I just measured the radius. And that's going to be the length I used this whole time. And as you can see, I wasn't 100% exact. It's hard to be on the computer. So mine's going to be a little bit off at the end. So I just went over to this point of intersection where the radius met the circle, and I just used the same distance to make an arc on the circle. And then I'm just going to move my compass over to where that arc intersected the circle, and I'm just going to make an arc there, an arc there, and now you'll probably get the pattern that I'm just moving around the circle. And you should end up with 6 equally spaced arcs. And if you did this correctly, the last arc should bring you back to where you started. And mine's not going to be 100% accurate. As you can see, mine's a little bit off. It didn't go exactly to where we started, because I'm doing this on the computer and it's awful on the computer. So it doesn't matter which 3 you connect, but just connect. And I'll just connect it here because I know it was supposed to end up here. So once again, mine's not going to be 100% accurate. Every other point. And then you have your equilateral triangle inscribed in the circle. Inscribed does mean that each of the vertex points do have to touch the circle. So if you need an equilateral triangle where the vertex points do not touch the circle, then it didn't give you the credit for this question because it does say inscribed in a circle. And then finally, the extra credit, which is not really extra credit because you do need to know how to do it, is to find the area of ABC. So we spoke about how we could box the triangle, and we could box it so that all of the vertex points are enclosed in the box. And then we have 3 right triangles, 1, 2, 3, and we can find the area of the whole box. We can find the area of the right triangles, and then we can subtract to get the area of the triangle that we want. So first I'm going to find the area of the whole box. Let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9. And 1, 2, 3, 4, 5, 6, 7, 8. So that's 9 times 8, which is 72. So the area of the whole box is 72. I'm going to find the area of triangle 1 now. Area of a triangle is 1/2 base times height. The base is 9, and the height 1, 2, 3, 4. So that is half of 36, which is 18. Next, we have the area of triangle 2, which is once again 1/2 base times height. Base is 2. Height is 1, 2, 3, 4, 5, 6, 7, 8. So that is half of 16, which is 8. And then finally, we have the area of triangle 3, which is 1/2 base times height. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. So that is half of 28, which is 14. So together, 18, 8, and 14 is 40. And if I do the whole box minus the right triangles, then I get the area, and 72 minus 40 is 32. So 32 is the area of the triangle that we're looking for, triangle ABC.